Iapetus, Saturn's mysterious moon, is slowly drifting into the giant planet's shimmering rings, moving at a speed of about 3.2 kilometers per second. And according to research from the Cassini spacecraft, this process may take millions of years to complete. Yet the effects it is already creating are producing changes in the ring system that are almost beyond imagination. Dust trails, fragments, and strange materials are being expelled, forcing scientists to confront urgent questions. Could Iapetus eventually become part of Saturn's rings? Or will this collision open a new era in our understanding of the universe? The mysteries surrounding Iapetus not only capture scientific attention, but also challenge our current knowledge of how the cosmos works. And the strange, paradoxical journey it is undertaking may hold the key to unlocking some of Saturn's deepest secrets. A silent yet powerful process has been unfolding for billions of years. A collision that produces no explosion, no violent shattering, but is persistent enough to reshape the ultimate fate of this moon. Its slowness and endurance are what make it so formidable. A mechanism unlike any type of impact humans usually imagine. And to understand it, we must step away from Iapetus's surface and look outward, toward a much smaller moon playing the central role, Phoebe. Phoebe orbits Saturn in a retrograde direction, a signature trait of a captured object, possibly originating from far beyond, perhaps from a region as distant as the Kuiper Belt. Its composition is rich in carbon, dark, cold, and fragile. For billions of years, impacts from micrometeorites have blasted countless dust particles from its surface. And over time, those particles did not disperse. Instead, they formed an enormous structure, the Phoebe Ring, the largest dust ring around Saturn, stretching from about 6 million kilometers to more than 12 million kilometers. Despite its extremely low density, its sheer size makes the total amount of dust substantial enough to influence any body passing through it. Iapetus orbits right inside the region swept by the Phoebe Ring. But the dust does not simply fall onto Iapetus by itself. It needs an invisible push, and that push is solar radiation. Photons streaming through the dust ring, colliding with each grain and producing a slow drag known as the Poynting-Robertson effect. As this force continuously acts on the dust, it loses orbital energy and slowly spirals inward. Meanwhile, Iapetus orbits Saturn in the prograde direction, while dust from Phoebe moves retrograde, creating a very high relative velocity between them. us. Every speck of dust, tiny and light as soot, strikes the leading hemisphere of Iapetus with enough energy to disrupt its microstructure and adhere to the surface. The effect is similar to a car speeding through the night. The windshield collects every insect in its path. On a cosmic scale, Iapetus is that windshield. A moon forced to plow through Phoebe's retrograde dust stream on every long orbit. The strongest evidence for this mechanism was recorded by the Cassini spacecraft during its close flyby of Iapetus in 2007. It detected a dark coating only a few centimeters to 1 meter thick, far too thin to be produced by any internal geological activity. Impact craters exposing bright, pristine ice beneath the surface made it clear the dark layer is not native bedrock, but a coating. A shell accumulated from the outside, particle by particle, molecule by molecule, over billions of years. Remarkably, orbital models from 2023-2024 precisely simulated Iapetus's current path through the Phoebe ring. And the results showed that its leading hemisphere lies exactly in the region of highest dust concentration. Meaning, Iapetus's orientation and rotation make it the perfect target for this incoming stream. But this collusion mechanism does not end with dust simply coating the surface. As the dark layer grows, it absorbs more sunlight, causing the darkened regions to heat up and trigger sublimation of the ice beneath. If this process continues for billions more years, models from 2024 predict that an average of 100 meters of surface ice could disappear every billion years. A tiny number on human scales, yet monumental when compared to the age of the solar system. This leads to a profound philosophical consequence. Cosmic collisions are not always explosive events. Sometimes the most transformative forces come from the gentlest touches. The quiet grains of dust without sound or light, which, when given time, become powerful enough to reshape a world. So, could Iapetus eventually disappear? Over time, its surface ice may erode, its structure may gradually weaken. And in the distant future, material stripped from Iapetus may become part of Saturn's ring system. As we move closer to Iapetus, we step into a paradox, a moon split in half by two opposing colors so extreme they appear as though they belong to entirely different worlds. The dark region, Cassini Regio, named after Giovanni Cassini, covers nearly 40% of the surface. With an albedo of only 0.03 to 0.05, equivalent to a tar-coated landscape. Every photon of sunlight that falls onto it seems to vanish without return. In contrast, the bright hemisphere reflects light with an albedo of 0.5 to 0.6. Nearly as bright as Enceladus, one of the most reflective bodies in the solar system. The two halves of this moon differ so drastically that if you place them side by side without context, you might easily believe they came from two separate worlds. On most moons, materials mix. Heat causes sublimation. Ice migrates, and solar wind erodes. Everything blurs the surface into gradual transitions of texture and color. But Iapetus breaks this rule. Its boundary between dark and light shows no transition from gray to shadow. Or from white to pale. Instead, it is a sudden, abrupt leap from bright ice to pitch black dust. Spectral data from the Cassini spacecraft, reanalyzed in 2023, revealed that the dark region contains high concentrations of carbon. Complex organic compounds, such as PAHs, and spectral signatures matching dust from the Phoebe ring, the massive dust structure surrounding Saturn and sourced from the retrograde moon Phoebe. This confirms that the dark coating is not native to Iapetus, it is an external layer. Yet this is only the surface of the mystery. The layer is astonishingly thin, measuring only a few centimeters to about 1 meter. The interplay of heat, ice, and time creates a cycle so slow it cannot be observed within a human lifespan. Because Iapetus rotates once every 79.3 days, one side faces the sun for extended periods. And it is precisely this Cassini region that absorbs the most solar heat. As the dark surface warms, the ice beneath begins to sublimate, releasing thin vapor from a world nearly motionless in every other sense. As the ice disappears, the dark dust becomes even more exposed, increasing absorption and driving the region into a self-amplifying thermal loop. This feedback cycle is what allows Cassini Regio to remain a deep, persistent shadow, sustaining itself over billions of years. Meanwhile, the sublimated vapor does not vanish. It migrates to the colder, bright hemisphere. There, the vapor freezes and accumulates as fresh layers of white ice, enhancing its powerful reflectivity. This implies a profound truth. The brilliant side of Iapetus was not gifted at birth. It was built slowly, molecule by molecule, over billions of years as drifting vapor settled into the cold. Physically, this means the bright hemisphere continues to brighten with time, while the dark hemisphere sinks deeper into blackness. Thermal model simulations published in 2022 showed that Iapetus possesses the strongest feedback cycle ever recorded on any body in the solar system. Here, light and darkness are not mere surface states. They are the results of an ancient battle between energy and matter, between heat and ice, between accumulation and erosion. What is astonishing is that this entire process unfolds in near silence. No violent collisions, no shattering ice cliffs, no volcanic eruptions. Only dust, sunlight, and time. Three subtle forces which, when woven together, create one of the most spectacular phenomena in any planetary system. However, this thermal feedback loop is only part of Iapetus's transformation. Because lying directly at the intersection of this stark light-dark divide is a geological structure science has yet to fully explain. An equatorial mountain range rising nearly 20 kilometers high, positioned absurdly precisely along the equator, stretching more than 1,600 kilometers. Between darkness and light, between the invisible cycles of erosion that span billions of years. Iapetus carries a signature so unusual that even NASA describes it as unlike anything we've ever seen in the solar system. A colossal equatorial mountain range stretching across nearly the entire circumference of the Moon. Standing upright like an ancient wall, dividing a world already split in two. No moon of Jupiter, no satellite of Uranus or Neptune. Not even the distant icy bodies of the outer solar system possess anything remotely comparable. Only Iapetus holds this giant spine, a wonder Cassini observed up close in 2007. Instantly recognizing it as a story that did not belong to any familiar orbit or ordinary geological process. The ridge spans 1,600 kilometers, is roughly 200 kilometers wide, and rises in some places to nearly 20 kilometers, taller than Everest in absolute height. What confounds scientists even more is its absurdly perfect placement. The ridge sits exactly along the equator, not even a single degree off. Precision nature rarely produces unless shaped by extraordinary events dating back to the earliest days of the solar system. There is no surface tectonics, no internal compression, no magma pushing upward from below. So what could raise a frozen wall thousands of kilometers long? Scientists propose two major hypotheses, and though they differ in mechanism, both lead to the same conclusion. The ridge is one of the oldest surviving features of Iapetus, possibly dating back more than 4 billion years. According to the traditional hypothesis, early Iapetus may have rotated far faster than it does today. Perhaps with a 16-hour day rather than the current 79.3 days. With such rapid rotation, centrifugal force would have been strongest at the equator, pushing outward on the moon's soft, mostly icy crust. If Iapetus' surface was still partially molten or weak at the time, its materials would not resist the outward pull. The moon would bulge like a fast-spinning sphere, forming a dense equatorial band. Later, as tidal interactions with Saturn slowed its rotation, the surface cooled and froze into the stretched shape, leaving behind a solidified ridge of ice. This model explains the ridge's great length, the walnut-shaped outline of Iapetus, and the similarity between ridge material and surrounding terrain. But how does a soft early structure preserve a height of 20 kilometers once frozen? And why would the bulge manifest as a sharply defined wall, rather than a broad equatorial swell, like those seen on fast rotating planets? These questions make the second hypothesis more compelling. In this scenario, a small moon of Iapetus, or another icy body, may have been torn apart by tidal forces, forming a miniature ring system around the moon, similar to Saturn's but vastly smaller. If this ring lay within Iapetus's Roche limit, its fragments could never reassemble into a new moon. Over time, orbital drag and interactions with the icy surface would cause the ring to collapse inward. Every fragment would fall in only one possible place, the equator. Modeling from 2024 shows that the height, width, and sharpness of the ridge align almost perfectly with the ring collapse scenario, a process that may have taken tens of millions of years. If this hypothesis is correct, then Iapetus once carried a ring of its own, and the equatorial ridge is not merely a physical remnant, it is historical evidence. It preserves traces of ancient, rapid rotation, the aftermath of a massive collision, the imprint of orbital instability, and possibly even the ghost of a moon that no longer exists. with no tectonic activity to erase it, no rain or wind to erode it. The ridge has survived nearly unchanged for billions of years. It stands there still, not only dividing the moon's surface, but dividing its history. Before and after Iapetus settled into the cold, still form we see today. Under Iapetus's conditions, ice at extremely low temperatures becomes incredibly strong, almost rock-like, and at around -143 degrees Celsius. Icy material can bear long-term stress without deforming. And without meaningful internal heat or periodic warming, the structure has preserved its shape for eons. The ridge endures because Iapetus is a world of absolute cold and absolute silence. Two perfect conditions for time to turn everything into stone. The equatorial ridge is not only Iapetus's greatest mystery, it is the key to understanding the moon's entire geological and orbital evolution. But the story does not end here, because this colossal wonder is also caught in the same slow cosmic erosion that is steadily reshaping the entire moon. At the heart of this thermal feedback loop lies a simple yet profoundly consequential fact. Iapetus has a day that lasts 79.3 Earth days. This forces every point on its surface to face sunlight for an unusually long stretch of time. There is no rapid day-night cycle like on Earth, no mechanism for quick cooling, no winds or atmosphere to redistribute heat. So once any region absorbs sunlight, it retains that heat long enough for irreversible changes to unfold. At Cassini Regio, the dark hemisphere, the extremely low albedo of 0.03 to 0.05 means sunlight is almost entirely swallowed. Though the total heat gained is still modest by Earth's standards, the surface remains tens of degrees below zero. But because water ice is the primary material composing Iapetus, even a small temperature increase is enough to trigger sublimation. Remarkably, the carbon-rich dust coating the dark region is only a few centimeters to at most 1 meter thick, according to Cassini's 2007 data. The ice beneath this dusty veneer is easily exposed to sunlight. As the ice sublimates, more dust is left behind, the dark layer grows thicker, and that means it absorbs even more heat. A 2022 thermal model concluded that Iapetus has the strongest thermal feedback loop ever recorded in the solar system. No planet, moon, or asteroid exhibits a cycle as stable and long-lasting. Under Iapetus's low gravity and extremely thin surface pressure, water vapor travels easily across the terrain like a ghostly drifting gas. And when it reaches the colder region, the bright hemisphere, it recondenses into fresh ice. This creates a phenomenon not observed on any other moon. Iapetus is actively transferring ice from its dark side to its bright side. If we imagine Iapetus as a living sphere, we can see it slowly shifting material from hot to cold, like a world breathing in slow motion. The recrystallization of ice on the bright hemisphere not only preserves its brightness, but steadily boosts its reflectivity over time. With an albedo of 0.5 to 0.6. The bright hemisphere functions like a massive ice mirror, bouncing away most of the sunlight and keeping the surface so cold that sublimation almost never occurs there. Thus, while the dark hemisphere gradually loses ice, the bright hemisphere is continuously replenished. A natural polarity maintained by the fundamental physics of ice, light, and vapor. Even more astonishing is that this feedback loop not only shapes color and reflectivity, it directly alters Iapetus's terrain. As ice sublimates, the surface becomes more porous and weaker, easier for dust to settle on, and more vulnerable to deformation from even small meteoroid impacts. The bright hemisphere behaves in the opposite way, more rigid, more stable, becoming a cold reservoir that stores the moon's redistributed ice. Philosophically, this reveals that polarization is not just a surface effect, it becomes a transformative force that reshapes the material structure beneath. The feedback loop is rewriting the face of Iapetus. Not with magma, not with quakes, but with light, shadow, and time itself. Through the Voyager and Cassini missions, a slow and unsettling truth emerged. This is not a typical moon of Saturn. But an object that defies every familiar logic of how icy bodies form and evolve. First, consider the density of Iapetus. only about 1.2 grams per cubic centimeter, significantly lower than Titan, Rhea, or Dion. This value reveals that roughly 75% of Iapetus is water ice, with the rest composed of light rocky material. There is no evidence that internal heating ever melted or differentiated its layers, meaning Iapetus has remained nearly unchanged since the moment it formed more than 4 billion years ago. Its shape deepens the mystery even further. When spacecraft captured global images of Iapetus, it appeared like a giant walnut, bulging dramatically at the equator. Such a figure can only form if, in the distant past, Iapetus once spun at incredible speed. Dynamic models suggest it may have rotated once every 16 hours, before tidal forces from Saturn slowed it to its present 79.3-day period. While Iapetus was still warm enough to be slightly malleable, its rapid spin would have caused the equator to swell outward once the surface cooled. That shape froze permanently into place. This is evidence that Iapetus underwent a formation history entirely unlike the other major moons of its era. But while its shape may be strange, its surface is even stranger. The density of impact craters, ranging from hundreds of kilometers across to innumerable tiny pits, reveals that Iapetus's terrain is profoundly ancient. Some regions may be 4 to 4.3 billion years old, nearly matching the age of the solar system itself. This is a world locked in stillness, one that has experienced virtually no geological activity for billions of years. No cryovolcanoes, no resurfacing, no internal flows. And then there is its orbit, at 3.56 million kilometers from Saturn. Nearly 3 times farther out than Titan, Iapetus sits beyond the strong influence of Saturn's magnetosphere and particle belts. This isolation makes it feel detached from the dynamic system that shapes the other moons, like a solitary fragment drifting on its own. Its orbital inclination, a steep 15 degrees relative to Saturn's equatorial plane, reinforces that idea. According to a 2023 analysis by JPL, this unusual tilt may signal that Iapetus was captured during the early solar system. This implies Iapetus may have formed elsewhere, perhaps in a region where small icy bodies were being scattered by intense gravitational interactions. Then, during the chaotic era of planetary migration, the period referenced by the NICE model. Iapetus was swept into Saturn's orbit and gradually settled into position. A world composed of 75% ice, without a clearly layered core, shaped like a spun-out object frozen mid-motion, carrying a surface almost as old as the solar system itself, and orbiting at a tilt so severe it seems as if it never truly belonged to Saturn. All of it forms a paradox. Iapetus behaves like a primordial ancient moon, yet it bears scars of dynamic forces from elsewhere. And from this long-standing strangeness, a phenomenon unlike anything else in the solar system emerged. The most extreme bright deck dichotomy known. It is not a temporary shift, as Giovanni Cassini once believed, but a deep, long-term consequence of its structure, orbit, and interaction with a surrounding sea of dust. The gravitational interaction between Iapetus and Saturn's ring system is not merely an intriguing astronomical phenomenon. It is a vivid demonstration of the universe's restless, ever-shifting nature. With its unusual orbit and steep inclination, Iapetus is undergoing a collision that moves slowly, almost imperceptibly, yet progresses in a direction that cannot be reversed as it grazes the outer edge of the rings. This gradual absorption of material and the reshaping of the ring's structure stand as living evidence that even the oldest satellites are never exempt from the dynamic laws governing their cosmic surroundings. The slow orbital drift unfolding over millions of years illustrates the fragility of structures that seem unchanging when viewed on human timescales. Although this process spans geological epochs, its final outcome is unmistakable. Iapetus, a solitary frozen world, is writing the last chapter of its cosmic story by merging into the grand architecture of its parent planet, becoming a testament to the laws of change and gravitational influence that shape every piece of matter in the deep expanse of space. This story reminds us that nothing in the universe remains still. Every world is moving toward an ending, shaped by gravity, time, and the slow fading of cosmic nature. Venus, the so-called sister planet of Earth, is, paradoxically, the most hostile world in the solar system. Its surface is hot enough to melt lead, its atmospheric pressure could crush a submarine, and the sky, thickly cloaked in clouds of concentrated sulfuric acid. Yet it was precisely this brutality that became the relentless challenge and obsession of the Soviet Union over 3 decades. From the early lost ventures of Venera 1, 2, and 3 to the historic success of Venera 13, the first craft to land on Venus, surviving 127 minutes on that infernal surface, sending back images, sounds, and chemical data never before captured. In 2012, a Russian scientist claimed that photographs from Venera 13 revealed a creature moving across Venus's surface. Although the scientific community dismissed this finding, it left a lingering question. Did the Soviets actually see something extraordinary on Venus? In this video, we rewind the clock and step into the Venera journey, where science, politics, and mystery collide. The Soviet Union's exploration of Venus through the Venera program was a relentless battle against the physical limits of matter and engineering. Venus, with its super-dense atmosphere, surface temperatures soaring to roughly 470 degrees Celsius, hot enough to melt lead, and pressures comparable to 92 atmospheres beneath Earth's oceans, became the harshest laboratory humans had ever attempted to conquer. Early Soviet attempts met with failure. The Venera probes 1, 2, and 3, launched between 1961 and 1965, could not complete their data transmission missions. Engineers quickly realized that standard designs were insufficient to protect delicate electronics from the planet's extreme heat and crushing pressure. Venera 3 became the first human-made object to impact the surface of another planet. But its inability to send back any data underscored the fact that surviving on Venus required not just landing, but a breakthrough in structural engineering and material science. The first major turning point came in 1967 with Venera 4. For the first time, a probe could descend into Venus's atmosphere while transmitting data throughout its entry. Venera 4 provided the first quantitative, direct measurements of atmospheric composition and structure. A technical triumph, but it was ultimately crushed by the planet's pressure before reaching the surface. The pinnacle of engineering success arrived with Venera 7 in 1970. Soviet engineers completely redesigned the lander module into a super-strong titanium sphere, reinforced to withstand pressures far exceeding initial estimates. This craft was built like a space submarine, with sensitive instruments packed safely inside a thick, pressure-resistant shell. Though it operated for only a brief 23 minutes. Venera 7 confirmed the planet's surface conditions and proved that human engineering could endure such extreme environments. In 1975, Venera 9 and 10 achieved another milestone. They sent back the first black and white photographs of Venus's surface. These images revealed for the first time a concrete landscape. Sharp, cracked rocks under a hazy yellow-orange sky, caused by the scattering of light through thick sulfuric acid clouds. Designing an optical system that could function under Venus's extreme temperature and pressure was an engineering feat far beyond the capabilities of any other nation at that time. The crowning achievements of the Venera program came with Venera 13 and 14 in 1982. Venera 13 set a record by surviving on the surface of Venus for 127 minutes. A period that seemed brief to us but represented a remarkable endurance under the planet's harsh conditions. During that time, it performed invaluable scientific tasks, capturing the first color images, revealing detailed views of gray-brown rocky terrain and a fiery orange sky. For the first time, humanity heard the sounds of another world, the faint whistling of wind through the dense atmosphere. Using a specialized drill, it collected surface soil samples and analyzed their chemical composition with X-ray spectroscopy, providing foundational data on Venus's geological history. If the technical achievements of the Venera program were a bold declaration, then the data it returned were a whispering mystery, a portrait of a forsaken world. For the first time, humanity glimpsed the surface of Venus, and what emerged was not only harshness, but a cascade of unanswered questions. The Venera probes 9, 10, 13, and 14 delivered historic images. These were not beautiful pictures, they were striking snapshots of a deadly world. Bathed in the dim orange-yellow light filtered through a dense atmosphere, the terrain appeared barren and desolate, far beyond what scientists had anticipated. Most striking were the sharp-edged rocks and fractured boulders, scattered across a surface seemingly coated with thick dust or sand. The existence of razor-sharp edges on these rocks remains a profound mystery. On Earth, wind, water, and other erosive forces quickly wear down sharp rock features. On Venus, though there is no liquid water, the superdense atmosphere behaves like a powerful fluid, generating winds strong enough to cause erosion. So why do these boulders retain their knife-like shapes? This implies that the geological processes that broke or formed these rocks occurred recently, or that some physical, chemical mechanism on Venus's surface is counteracting erosion. Decades later, the rare direct images from Venera still harbor unexplained signs. Some researchers, including former Soviet scientists, have pointed out unusual shaped objects appearing and disappearing between consecutive photographs of the same landing sites. Are these technical glitches, debris from the landers, or something stranger? The most intriguing hypothesis comes from a few scientists who speculated that the geometric structures or transient objects captured in the images could be evidence of the survival of some extreme form of life. Although the scientific community largely dismisses this possibility due to the planet's unbearable temperature and pressure, the curiosity persists. What caused the strange spots or faint lines in Venera 13's color images? Today, we cannot easily land probes on Venus, but technology has advanced in another direction: remote observation. Advanced space telescopes, like James Webb, alongside radar missions from NASA and ESA, have returned to study Venus. James Webb, using specialized infrared wavelengths that can penetrate certain cloud layers, investigates the chemical composition of the atmosphere and even surface reflectivity in the regions previously explored by landers. Modern radar tools, particularly the radar from the Magellan mission, have provided detailed topographic maps of 98% of Venus's surface, identifying volcanoes, plains, and massive tectonic cracks. What Venera captured, a faint dust layer and razor-sharp rocks, remains uniquely irreplicable by radar. Scientists are working to use this data to accurately decode which materials create the unusual reflectivity that radar and JWST detect, especially in elevated terrains. This makes the images from the 1970s more valuable than ever. They are surviving fragments of a vast puzzle. A reminder that we have only just begun to touch the edge of Venus's mysteries. While the scientific data from the Venera missions overwhelmingly indicate the impossibility of life on Venus's surface, A sensational claim emerged decades later, challenging the scientific consensus and sparking public curiosity. This is a story about how low-resolution images, captured under extreme conditions, can be interpreted in multiple ways. In 2012, Dr. Leonid Kassan-Fomalidi, a veteran scientist from the Russian Space Research Institute, who had directly participated in the Venera missions, published a controversial finding: reanalyzing images taken by Venera 13 in 1982. He claimed to have detected objects that appeared to move and change shape between consecutive frames taken minutes apart. Most strikingly, Kassan-Fomalidi pointed out a complex-shaped object resembling an arthropod, appearing in one frame and vanishing in the next. He suggested that this could be evidence of an extremophile life form capable of surviving Venus's extreme temperatures and pressures. Perhaps through a physical or chemical structure entirely alien to Earth-based biology. However, the international scientific community almost entirely dismissed this claim, attributing it to misinterpretations and technical artifacts. The Venera images were extremely low resolution and underwent heavy compression to transmit across interplanetary distances to Earth. Faint details and ambiguous shapes were easily misread. The most widely accepted explanation is that the object was merely a protective shell, or a piece of equipment dislodged from the Venera 13 lander during descent. The apparent movement could have been caused by wind or minor shifts of the lander itself. Human brains naturally seek familiar patterns, especially shapes resembling humans or animals. The arthropod could simply have been a rock illuminated to create a scorpion-like illusion. The debate reignited in 2020 with a groundbreaking scientific announcement: the detection of a significant concentration of phosphine gas in Venus's clouds, about 20 parts per billion. Phosphine is a toxic gas that, on Earth, is primarily produced by anaerobic biological activity or industrial processes. Analysis indicates that no known chemical or physical process, volcanism, lightning, or mineral reactions, could generate phosphine at the observed concentrations in Venus's atmosphere. This makes phosphine a potential biosignature, suggesting that an unknown microorganism may exist and thrive in sulfuric acid droplets. Using an extraordinarily unique energy metabolism to produce phosphine as a byproduct. Despite the compelling evidence, skeptics have pointed out two nearly insurmountable chemical and physical barriers: water activity and acidity. Venus's clouds contain no liquid water, only concentrated sulfuric acid droplets. To survive, any organism would need a protective shell or an entirely novel chemical mechanism capable of replacing water as the main intracellular solvent. A phenomenon never observed in Earth-based biology. Perhaps the greatest barrier is the extreme scarcity of free water. While sulfuric acid contains water, most of it is chemically bound. The available water for biochemical reactions in Venus's sulfuric acid droplets is extremely low. For comparison, even the most drought-tolerant organisms on Earth require an AW of at least 0.585 to maintain enzyme and membrane function. Venus's environment is hundreds of times drier than the survival limit of any known organism. To reconcile the presence of phosphine with Venus's harsh environment, scientists have proposed bold biological models. One hypothesis suggests that microbes may survive in the clouds, but when carried downward into hotter, more acidic layers, they enter a dormant, spore-like state. High winds then return them to milder layers, where they reactivate and reproduce, creating a continuous survival cycle. An even more extreme hypothesis is that Venusian life may have evolved a biochemistry not based on water as the primary solvent, possibly using concentrated sulfuric acid or another compound to form stable structures resistant to corrosion. New missions, especially NASA's Deep Atmosphere Venus investigation of noble gases, chemistry, and imaging, will deploy probes into the atmosphere. The mission's primary objective is to precisely measure phosphine and trace gases, along with analyzing the composition of cloud droplets and H2O at different altitudes. This analysis delves deeply into why the cloud layers are considered potentially habitable and the chemical barriers any life form would have to overcome. Studying Venus cannot be separated from the study of moving objects in the solar system, as both serve as prime examples of physical interactions in extreme environments. Comics like Atlas become invaluable references. Atlas is a remarkable example of how icy material interacts intensely with its surrounding space environment. As it approaches the Sun, it is influenced not only by gravity but also by electromagnetic radiation and solar wind. One of the greatest challenges for settling Mars is the lack of a global magnetic field and a thin atmosphere. Leaving the Martian surface exposed to high doses of dangerous ionizing radiation. By contrast, Venus offers natural shielding. The atmospheric density at around 50 kilometers altitude is sufficient to absorb most high-energy particles. Radiation levels there are estimated to be comparable to or lower than what astronauts experience aboard the International Space Station in low Earth orbit. This eliminates the need for thick, heavy, and expensive radiation shielding such as rock or water layers used on Mars, significantly simplifying module design and construction costs. Gravity differences are a critical factor for the long-term survival of humans in space. Surface gravity on Mars is only about 38% of Earth's. Prolonged low-gravity or microgravity environments cause severe biomedical issues, including muscle atrophy, bone loss, vision impairment, and immune system changes. On Venus, settlers would experience an environment nearly compatible with human physiology, greatly reducing health risks related to bones and muscles, making Venus an optimal biomechanical choice for permanent settlements and human reproduction in space. At the 50-kilometer altitude, temperatures range between 27 degrees Celsius and 37 degrees Celsius. The pressure is near 1 atm, a major engineering advantage. Floating structures do not need to withstand large pressure differentials. Instead of designing rigid pressure suits or modules capable of withstanding extreme pressures. Settlers would only require cabins equipped with chemical filtration and basic respiratory support to protect against sulfuric acid vapors. Because breathable gas is much lighter than the surrounding atmosphere. A massive balloon filled with breathable air could generate significant lift, allowing it to float and maintain altitude without continuous energy expenditure. The greatest engineering challenge lies in composite material design for the balloon's shell. The outer layer must meet three simultaneous requirements: resist concentrated sulfuric acid in the clouds, handle structural loads and high-speed wind forces, and withstand degradation from intense ultraviolet radiation, especially at higher atmospheric levels. Teflon or high-grade fluorocarbon polymers are the top candidates. Kevlar or carbon nanotube composites would be integrated to withstand structural loads and strong winds. Venus's potential for future exploration extends beyond the solar system. Venus serves as an ideal model for studying Venus-like exoplanets, particularly tidally locked worlds. Venus is a textbook example of a planet that has surpassed the water evaporation threshold and become trapped in an irreversible thermal loop. Studying noble gases and hydrogen isotopes in Venus's atmosphere through missions like Da Vinci Plus is key to understanding exactly how a once habitable planet transitioned into a hellscape. Venus's super-rotation mechanism enabled scientists to model heat and energy transfer on tidally locked exoplanets. On these worlds, the day side is scorching while the night side is frozen. Super-rotation distributes temperature evenly, showing that a dense atmosphere can act as a self-regulating mechanism, making the habitable zone on tidally locked planets more temperate. In summary, Venus is not just a destination, it is a cosmic control station, where advanced engineering challenges will open the door to humanity's long-term habitation of the galaxy. Looking back at the journey of exploring Venus, we can see that the Soviet Venera missions achieved a true milestone. Becoming the first human-made objects to successfully land on the surface of another planet. From this, we understand that Venus serves as a natural laboratory of extreme chemistry. Its thick sulfuric acid clouds, acid rain, and carbon dioxide-rich atmosphere have transformed the planet into a blazing furnace, a stark contrast to the planet's primordial beginnings. The Soviets once claimed to have observed moving structures resembling life in the old Venera images. But the international scientific community largely dismissed these as technical errors caused by image interference or rock formations eroded by wind. Recently, however, the discovery of phosphine, a potential biosignature in the cool upper clouds, has reignited the debate over life on Venus. Venus, our enigmatic second home, is poised for rediscovery. With upcoming NASA missions such as Da Vinci Plus and Veritas, we will, for the first time, send probes flying through its clouds to analyze and map its geology in unprecedented detail. Tracking these missions is not merely a scientific endeavor, It is an effort to probe the boundaries of life itself, to uncover the mysteries the Soviets left behind, and, most importantly, to gain insights into climate processes that could help us protect our own Earth Proxima Centauri, the closest star to us, lies 4.2 light-years from Earth, a vast distance that takes an immense amount of time to cross. If we are to leave the solar system, we must confront two major challenges. First, the speed achievable with current technology, chemical rockets, is simply not enough. Second, the energy required would have to be thousands of times greater just to overcome the sun's immense gravitational pull. Research into ion engines, nuclear fusion propulsion, and bold ideas such as warp drives that could bend space-time in the future is gradually moving forward. However, these technologies remain only the first steps of a long journey, still facing countless physical and engineering barriers. And if one day we truly achieve this, could humanity evolve to adapt to the harsh conditions of outer space? Behind these questions about technology lies something far greater. Let us look toward a future where we may come closer to what once seemed impossible. The solar system is encased within protective, invisible bubbles. These are the heliosphere and its outer edge, the heliopause. The heliosphere is the vast region where the solar wind interacts with the thin gas and particles of interstellar space, forming a protective shield around our planetary system. The heliopause marks the ultimate boundary of the sun's influence, the point where the solar wind's pressure fades, no longer strong enough to overcome the push of the interstellar medium. NASA's Voyager 1 and 2 probes delivered astonishing insights into these remote frontiers. When Voyager 1 crossed the heliopause in 2012, it entered a region far denser with plasma than scientists had predicted, where powerful interstellar magnetic fields pressed back against the heliosphere. Later, Voyager 2 revealed that this edge is not a smooth boundary, but a turbulent, dynamic transition zone. These discoveries not only transformed our understanding of the solar system, but also underscored the immense challenge of breaching this invisible wall. Beyond the heliosphere lies the Kuiper Belt and the enigmatic Oort cloud, which redefine the true scale of our solar system within the Milky Way. The Kuiper Belt, located beyond Neptune's orbit, is a vast expanse filled with billions of icy bodies, the birthplace of many short-period comets. Here, distances between objects are staggering, highlighting the incredible stretches that even light must traverse. It takes about 5 hours for sunlight to reach the Kuiper Belt's edge. Farther still, on the outermost rim, drifts the Oort cloud. A colossal, spherical shell of trillions of frozen objects and rocky fragments, believed to be the source of long-period comets. It may extend to nearly a quarter of the distance to the nearest star. Meaning light from the sun would require thousands of years to cross it and thousands of years to reach the Oort cloud. Exploring the Kuiper belt and the Oort cloud is more than a scientific endeavor. It is an active perspective, placing the true scale of our solar system against the vast backdrop of the Milky Way. Yet the sheer distance to the Oort cloud's edge illustrates the staggering challenge ahead. A journey beyond this frontier would demand unimaginable energy and time, far beyond the capabilities of our current technology. This boundary is not just a physical barrier, it is an invitation, a silent call to explore the unknown. Once we grasp the invisible boundaries of our solar system, the next question emerges. Just how vast is it really? To comprehend its scale, we must first consider the distances between its planets. From our small Earth to the massive Jupiter is already an enormous journey. But to reach the edge of the Oort cloud, that distance stretches into something almost unimaginable. The closest star to us, Proxima Centauri, lies only 4.2 light-years away, and yet, in reality, the numbers are staggering. Voyager 1, traveling at a breathtaking speed by human standards, would need about 75,000 years to get there. That's longer than the entire span of human civilization. The problem of time is not merely a matter of physics, it's a profound concept that shapes our perception of reality. Can humanity afford to wait thousands of years to witness the results of interstellar exploration? Time is not just a constant flow, it bends, it warps depending on motion. According to Einstein's theory of time dilation, as an object approaches the speed of light, time slows relative to everything else. This opens an extraordinary possibility. If we develop technology capable of near light speed travel, could human experience of time transform entirely? Perhaps in the future, as technology advances, we will discover ways to overcome these immense distances, turning dreams of interstellar exploration into reality. But to achieve that, we must first confront the challenge of time itself, an inescapable factor intertwined with humanity's quest to conquer the cosmos. To embark on an interstellar journey, a spacecraft must overcome gravitational forces, first of its home planet and ultimately of the Sun itself. This requires achieving a specific change in velocity known as delta V. For Earth, the delta V needed to break free from the Sun's gravitational grip is staggering. It demands an almost unimaginable amount of energy to accelerate a spacecraft of any significant mass to such speeds. Here lies the greatest limitation of current technology: chemical rockets. These engines, while powerful enough to take humans to the moon and send probes across our solar system, are extremely inefficient. They lack the thrust and energy capacity to sustain long-during missions beyond the confines of our stellar neighborhood. To overcome this barrier, scientists are pursuing advanced propulsion systems, ion engines, nuclear fusion drives, and even the speculative warp drive. Ion engines, which use plasma to generate a steady, gentle thrust, are far more efficient than chemical rockets. Yet their low thrust means they are suitable only for missions within the solar system, not for achieving interstellar speeds within a human lifetime. A more promising, yet highly challenging solution lies in nuclear fusion propulsion. This technology seeks to replicate the process, powering the sun, fusing light atoms to unleash colossal energy. If realized, it could deliver unprecedented propulsion, enabling spacecraft to reach extraordinary velocities. But here's the catch. Controlling fusion for clean energy on Earth remains one of science's greatest hurdles. Miniaturizing it for a spacecraft engine is an even greater feat. And then there is the boldest concept of all, warp drive, a theoretical engine that would bend space-time around a spacecraft, allowing faster-than-light travel without breaking the laws of physics. In the meantime, spacecraft have relied on a clever workaround: gravity assist. By harnessing a planet's gravitational pull, probes like NASA's Voyager gain speed without expending extra fuel, slingshotting past Jupiter to accelerate on their journey. Yet even this ingenious maneuver only adds a few kilometers per second, nowhere near what's needed for interstellar flight. The interstellar medium is a vast expanse filled with unseen dangers. Once we leave the protective bubble of the heliosphere, spacecraft and any humans aboard will face a relentless storm of cosmic radiation and high-energy particles, primarily protons and heavy nuclei. These particles can pierce spacecraft hulls, inflicting severe damage on electronics and, more critically, on human health. They can alter DNA, raise cancer risks, impair cognition, and even lead to death. A striking example is Voyager 1, which encountered magnetic field conditions it had never experienced before as it exited the solar system. Add to that the extreme cold of interstellar space, and the challenge grows. Developing shielding effective enough to protect both machines and humans without adding prohibitive mass is an immense engineering hurdle. Interstellar space is also strewn with tenuous clouds of gas and dust. While their density is low, at interstellar speeds, even a tiny dust particle becomes a hypersonic bullet, capable of tearing through a spacecraft's hull. Protecting against these high-velocity impacts demands entirely new material designs. Ones that can self-heal or withstand catastrophic shocks. Another formidable, yet less obvious, barrier is communication. Light and radio waves travel at finite speeds. The farther a spacecraft ventures, the longer it takes for signals to reach it and return. To the nearest star, Proxima Centauri, a radio message would take over 4 years to arrive. Creating an enormous delay in command and data transmission. Maintaining reliable communication across such distances while combating interference and signal loss remains a puzzle without a clear solution. All these elements combine to make interstellar space a domain where invisible barriers are not merely technical challenges, they are matters of survival. To conquer this realm, we will need more than powerful engines. We will require materials never before created, unprecedented shielding systems, and the adaptability of human beings to endure the harshest extremes of the cosmos. Scientists are relentlessly pushing the boundaries of technology, driven by the hope of unlocking the door to unimaginable adventures into deep space. One of the most ambitious concepts is Breakthrough Starshot, a bold vision for a fleet of thousands of tiny spacecraft. Each weighing just a few grams, equipped with enormous light sails. The plan: fire powerful laser beams from Earth to accelerate these sails to astonishing speeds, up to 20% of the speed of light. At that velocity, a nanocraft could reach Proxima Centauri in just 20 years, carrying cameras and sensors to transmit data back home. Enormous engineering challenges remain, from building lasers powerful enough to sustain such acceleration, to stabilizing the sails, to ensuring communication across such vast distances. Yet this project proves that humanity is beginning to think beyond the confines of traditional rockets. Even further into the realm of science fiction are concepts like warp drives and wormholes. Alcubierre's warp drive remains an elegant hypothesis, bending space-time to allow faster-than-light travel without breaking local physical laws. Wormholes, on the other hand, propose shortcuts through space-time, tunnels that could link two distant points in the cosmos. For now, both require physical conditions never observed and exist only within the realm of theoretical physics. Space agencies like NASA, ESA, and JAXA, together with private pioneers like SpaceX, are joining forces to push the limits of human capability. Sharing knowledge, pooling resources, and uniting under a common vision will be essential, because interstellar travel is not the ambition of one nation. the collective dream of humankind. Among the boldest concepts in interstellar travel is the generation ship. More than just a vessel, it represents a profound symbol of hope and humanity's unyielding desire to uncover the mysteries of the cosmos. This idea stems from a harsh reality. Even journeys to the nearest star systems, such as Alpha Centauri, could take decades or even centuries. A generation ship would therefore need to sustain life for multiple generations, creating a self-contained world capable of supporting an entire society on a voyage across the stars. One of the greatest challenges lies in maintaining a stable, closed-loop ecosystem within the confines of a spacecraft. Scientists are exploring systems where water, air, and food can be recycled and regenerated using only onboard resources. Projects like Biosphere 2, an ecological experiment in Arizona, offer a glimpse into this challenge. A miniature world where air, water, and food had to be continually renewed without any external input. Ensuring resource sustainability, managing waste, and resolving technical failures over hundreds or thousands of years is a problem with no precedent. A single error could trigger catastrophic consequences. Energy systems represent another critical component. Nuclear power, solar energy, and even nuclear fusion, the very process that powers the stars, are being considered as potential sources to sustain such long-term missions. Fusion, if mastered, could provide an abundant and virtually limitless energy supply, drastically reducing reliance on conventional fuels and ensuring the viability of these epic journeys. Yet perhaps the most formidable challenges are not technological, but psychological and social. Isolation, confinement, and the intricate dynamics of a tightly knit community in an artificial world will test human endurance in ways we can barely imagine. What happens when generations live and die without ever seeing a real night sky or feeling the wind on their faces? How will humanity cope with monotony, cultural drift, and the inevitability of interpersonal conflict? Over time, will the original mission retain its meaning, or will it fade, distorted by the pressures of survival? Research into group psychology under extreme conditions, such as Antarctic expeditions and short-duration space missions, offers crucial insights. Ultimately, the dream of a generation ship is not just a feat of engineering. It is a journey into the deepest questions of who we are, what we value, and how far we are willing to go to claim our place among the stars. This is the point where we approach an entirely new frontier, the place where biology meets technology. Will humanity evolve to adapt or transform completely to survive? Evolution is a natural process that unfolds over millions of years. Yet in the context of deep space travel, that timeline could be forced to accelerate. Research suggests that humans possess the genetic flexibility to adapt to environmental changes. For instance, people living in high-altitude regions often develop physiological traits such as larger lungs for more efficient oxygen absorption. Similarly, if humans were to live in environments with high radiation or low gravity, new genetic traits could emerge to aid survival. One of the greatest threats in deep space is cosmic radiation, a relentless force that can damage DNA, causing disease and functional decline. To counter this, the idea of genetic engineering to enhance radiation resistance has entered serious discussion. Imagine a generation of astronauts genetically modified for superior cellular repair, cancer resistance, or even skin and organs capable of withstanding intense radiation. This is no longer pure science fiction. Technologies like CRISPR to Cas9 are opening unprecedented doors to altering the human genome. Living in low-gravity environments poses another major challenge. Studies on astronauts show that prolonged weightlessness leads to muscle atrophy and bone density loss. Over time, this could drive the evolution of lighter skeletons, bones strong enough to function but adapted for minimal gravitational pull. Beyond biology lies an even more radical possibility: the fusion of man and machine. If the organic body proves too fragile against the extremes of space, why not replace it? Cyborgs, half human, half machine, could endure radiation, extreme temperatures, and the vacuum of space in ways biological organisms never could. Imagine a human brain integrated into a robust mechanical body, or even merged into a fully synthetic AI system. And if artificial intelligence becomes so advanced that it develops consciousness and self-improvement, could AI become the ultimate successor for interstellar exploration? Machines do not fear radiation, require no oxygen, food, or water, and could function flawlessly for millions of years. They might be the perfect astronauts for journeys spanning eternity. But then comes the haunting question. If we alter our genes beyond recognition, If we abandon flesh for steel, what remains of our humanity? The definition of identity, consciousness, and purpose will be pushed to the brink. The voyage beyond the solar system may not just be a quest for new worlds. It could become a profound journey to rediscover who we are and whether we are willing to surrender parts of our essence to achieve the impossible. Interstellar travel is not a matter of the next few centuries. The barriers, physical, technical, and even biological and social, stand tall before us. Solutions like the generation ship or altering human nature pose profound ethical and philosophical challenges that humanity must confront. Yet, it is this very dream, the dream of pushing beyond known limits, reaching distant stars, that defines what it means to be human. It symbolizes our innate thirst for discovery, understanding, and transcending ourselves. Since the dawn of civilization, humans have always looked up at the mysterious night sky, wondering about their place in the vast universe. It is this relentless curiosity that has driven us to develop science, technology, and philosophy. Space exploration, in a deeper sense, is a journey of self-discovery. Whether or not we truly leave the solar system in the next few millennia, the quest for answers fuels our strongest motivation, pushing us to grow, to dream, and to strive endlessly. Perhaps in this unending journey, we will find deeper meaning in our existence within this mysterious cosmos.
orbital drift unfolding over millions of years illustrates the fragile structure of the
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.